In this activity, we're going to be looking at infinite series and manipulating those series to create new series for new functions. In order to do so, we need to know some basic series. So we're going to start with the most basic infinite series, and that's the one for our very simple geometric sum. This is of the form a over 1 minus r. So this is a geometric series with first term 1 and common ratio opposite x. So we can now produce the terms of the series by starting at 1 and multiplying each term by the opposite of x. And we produce the series 1 minus x plus x squared minus x cubed, and so on. When you write series, you should get in the habit of writing the first few terms as well as an expression for the general term as you continue on. So here we have negative 1 to the n, x to the n, and so on. Also, when we have an alternating sign, I like to pull off the negative 1 as its own term so we don't confuse it when we do some of the manipulations that will follow. Another term you should be familiar with is how to produce the general term of the Taylor series. And so the general term for our Taylor series looks like the nth derivative at some value a being what we call the center of our series, times x minus a to the nth over n factorial. And we're going to apply this expression to build another one of our very basic series, and that is the series for sine. Sine, we know, has derivative at 0 of 1, 0, or negative 1. And so we start out with our functional value at 0. We're going to develop this series around 0. Functional value of sine at 0 is 0, so we have no constant term. First derivative of sine at 0 is 1, so that becomes the coefficient, part of the coefficient of our first term. We end up with our first term of x. Next derivative would be 0. Derivative after that, we're up to the third derivative, would be negative 1. So we have negative x cubed over 3 factorial, and so on. Odd degree terms have coefficients of 1 or negative 1 over the appropriate factorial, and even degree terms have coefficients of 0, so we don't even write them. Negative 1 to the nth, x to the 2n plus 1 over 2n plus 1 factorial, and so on. And there's the series for sine. All right, let's start manipulating. First manipulation we're going to look at is taking derivatives. Well, if we take the derivative of sine, we should get cosine, or we will get cosine. And so what comes out when we differentiate our series is just a string of, it's an infinite polynomial, and so we can differentiate term by term. And the derivative of x would be 1. The derivative of x cubed would be 3x squared, and drag along that denominator part of the coefficient, followed by 5x to the 4th over 5 factorial, and so on. When we get out here to the nth term, remember we're not differentiating with respect to 1 or n, but with respect to x, so the negative 1 to the nth does not change. And that becomes 2n plus 1 times x to the 2n all over 2n plus 1 factorial, and so on. And when we simplify the terms of this expansion, we get the series for cosine. Gives us a little practice in reducing with factorials, x to the 4th over 4 factorial, and so on. So negative 1 times x to the 2n over 2n factorial. That should be a minus sign the next term. We can convince ourselves that this is a good series for cosine. Cosine itself is an even function, and all the terms in our series have even degree. We know the cosine of 0 is 1. So this, and each term follows the pattern for the Taylor series, for the general term of the Taylor series. So we see that differentiating a known series will produce a series for a new function. Other way to manipulate things using calculus would be to integrate. So let's go back to sine and integrate sine. We know what to expect. The integral of sine with respect to x is the opposite of cosine plus a constant. So now if we do some moving of the terms before we actually do our integration, we'll see what we end up with will be cosine equals some constant minus the integral for sine. Going back to our series for sine and integrating term by term would generate cosine x equaling some constant minus. Antiderivative of x would be x squared over 2. Antiderivative of x cubed would be x to the 4th over 4, and then times that denominator of 3 factorial. Antiderivative of x to the 5th would be x to the 6th over 6 times 5 factorial, and so on. And when we get out to our general term, negative 1 to the n, x to the 2n plus 2 over 2n plus 2 times 2n plus 1 factorial, and so on. And simplifying each of these terms, combining the denominators into new factorials, and also evaluating for our constant, we know that the cosine of 0 is 1, and the polynomial terms of our series will produce a value of 0 when x is 0. So our constant is also 1. And in fact, we end up with the same series we had earlier. Cosine x is 1 minus x squared over 2, or 2 factorial, plus, remember we're distributing this subtraction, x to the 4th over 4 factorial minus x to the 6th over 6th factorial, and so on. When we get out here to the nth term, we have x to the 2n plus 2 over 2n plus 2 factorial. Usually it's easier to stop not at the n plus first term, but at the nth term. So we'll go to the term right before that, negative 1 to the n, x to the 2n over 2n factorial, and so on. And we had our sign changes, so we have the appropriate sign for our negative 1. In the activities that follow, you will be integrating and differentiating new series.